Okay, yeah. So, hi everyone. So, good morning all. Right. So, let me know whether audio and video everything clear here. Everything clear. See, if it is not clear, please comment in chat box. Right. Okay. So, I hope audio and video everything is clear. Right. Okay. Yeah. So, we are dealing with the subject electromagnetics. Right. So, in the previous session here, we have seen the nature of wave here. In the previous session, we have seen nature of wave. So, mainly that is nothing but what? That wave is nothing but transverse wave. Yes or no? So, we have studied about transverse wave. So, what do you mean by transverse wave and how to represent the transverse wave mathematically? So, these things we have seen in the previous session. Understood? Okay. So, what we have understood by transverse wave here? See, whenever you create a disturbance at some particular location, so that disturbance is going to whenever you create, let us say, if you consider a particle, so if you drop a stone into that, let us assume this is water medium here. So let us assume you have dropped a stone, into that water medium. So then what will happen here? So this particle will start what? This particle will start oscillating up and down. So since all the water particles are interconnected to one another, so what will happen? So after some time, this oscillations will be transferred to next particle, and this particle will set into oscillation. So after some time, this disturbance will be transported to what? Transport to next particle, and this particle will set into oscillation. So after some time, if you observe the water, each and every particle in the water medium is going to oscillate. It is oscillating up and down. Understood? Okay. So here, if you form a plane here, you can observe that the oscillations are occurring in a plane, and these oscillations are shifting from one location to another location in a direction perpendicular to what? Perpendicular to this plane. Okay. So this plane we call it as what here? Transverse plane, right? Okay. And these oscillations are shifting, or this disturbance is shifting from one location to another location in a direction perpendicular to what? Perpendicular to transverse plane. So this type of wave propagation we call it as what here? This type of wave propagation we call it as transverse wave. Understood? Here you are having the oscillations in transverse plane, and the shifting of these oscillations will be in perpendicular to what? Perpendicular to this transverse plane. So this type of motion we call it as what here? Transverse wave. So if the oscillations and propagation, if both are in the same direction, then we say it as what? We can say it as longitudinal wave, right? Okay. Okay. Then we can say it as longitudinal wave. So here our electromagnetic wave is transverse in nature here, Okay. So that's why we have studied about transverse wave, right? Okay. So next year, so we have seen how to represent this transverse wave. So this transverse wave simultaneously is going to have two motions. One is oscillatory motion in a transverse plane, and another one is what? Another motion is nothing but the shifting of these oscillations, or the propagation of these oscillations will be perpendicular to what? Perpendicular to the transverse plane. Understood? Okay. So all these things we have covered in the previous session itself here, right? And also we have seen that any function which is of this form, that is f of some constant beta into plus or minus x plus or minus vt, will represent what? Will represent a wave function. It represents what here? Wave function. So any function which is of this form will represent what here? Will represent a wave function. Now, how to determine whether this wave is propagating in positive x direction or negative x direction, like that? I have told you a trick here how to tell that. See, just observe the polarity before x and observe the polarity before vt. Understood? So if the polarity before x and the polarity before vt, if both are same, then the wave is propagating in negative x direction. If the polarity before x and polarity before vt, if both are of opposite polarity, then the wave is propagating in positive direction. Understood? So these things we have seen in the previous session itself. So this is the general representation here. This is the general representation of a wave function. So any function which is of this form will represent what? Will represent a wave, right? Okay. Okay. So now see here. So let us consider let us consider this function here. Let us consider this function f of beta into x minus vt, x minus vt. Understood? Okay. So f of beta into x minus vt. See, it is a function of what? It is a function of both space as well as what? As well as time. Right? Okay. Now, if I differentiate this function with respect to space here, with respect to x, right? See, if the function is only a function of one variable, that is, if it is a function of only x here, if it is a function of only x, okay, then we call it as what? One-dimensional wave. If it is a function of x and y, then we call it as two-dimensional wave. If it is a function of x, y and z, then we call it as a three-dimensional wave. Understood? So first we are dealing with one-dimensional waves here. Okay. Okay. So now see here, if I differentiate this function with respect to x, if I differentiate this function with respect to x, what I am going to get here? So let us say dou f by dou x, dou f by dou x. So if I differentiate this, what I am going to get? So with respect to x here, with respect to x, if you differentiate, I am going to get just write down this one in this manner. Okay. So f of beta into what? F of beta into, let us take vt minus x, x minus vt or vt minus x, it doesn't matter, right? Okay. So dou f by dou x is equal to what? If you do the differentiation with respect to x, what you are going to get? You are going to get minus beta into what? Into f dash of what? F dash of beta into vt minus x, vt minus x. Understood? Now, if I differentiate again this function with respect to x again, so then what I am going to get here? Dou square f by dou x square is equal to what? What you are going to get here? You are going to get here minus beta whole square into what? F dash of what? F double dash of beta into vt minus what? Vt minus x, right? Okay, so I have differentiated the function twice here with respect to x. Now similarly, if I differentiate the function with respect to time, what I am going to get here? What I am going to get, if you differentiate this function with respect to time, what you are going to get? You are going to get beta into v into what? F dash of beta into vt minus what? Minus x. Okay, now again differentiate this function with respect to time here. Again differentiate this function with respect to time. So what you are going to get here? Again differentiate this function with respect to time. You are going to get what? You are going to get beta v whole square into what? Into f dash of what? F dash of beta into vt minus x, Understood? Okay, so let us consider this as equation 2 and let us consider this as equation 1. Okay, now if I do 1 by 2 here, if I do 1 by 2, so what you are going to get? Tell me what you are going to get. If I do 1 by 2, so that is dou square f by dou x square divided by what? Dou square f by dou t square. Remember here f is a function of what? F is a function of x and t, right? F is a function of x and t. Okay, so this is equivalent to what? This is equivalent to what you are going to get. So here you are having minus beta whole square into what? F double dash of beta into vt minus x, So divided by what you are having here? Beta v whole square into f double dash. See, this is f double dash here, right? Okay, you are differentiating twice. So f double dash of what? Beta into vt minus what? Vt minus x. Understood? So what you are going to get here? F double dash beta of vt minus x and here f double dash of beta of vt minus x will get what? Will get cancelled. So here beta square and here beta square will get what? Will get cancelled. So therefore I can write the above expression in this manner: dou square f by what? Dou square f by dou x square. So every time I don't write it is a function of x and t like that. Okay, you have to understood that it is a function of x and t. Right, so dou square f by dou x square is equal to what? Is equal to what you are going to get here? What you are going to get? What is left out? Tell me. 1 by v square. Yes or no? Beta square I have cancelled. Right. What you are having? V square. Right. So this one is beta square into v square. Beta square will get cancelled. So what is left out here? 1 by v square. This is cancelled. So I am sending dou square f by dou t square to this side. So I am going to get dou square f by what? Dou square f by dou t square. Understood? So dou square f by dou x square is equal to what? Is equal to 1 by v square, 1 by v square into dou square f by dou t square, where v represents what here? V represents a velocity of what? Velocity of the wave, velocity of wave. Yes or no? So this dou square f by dou x square is equal to 1 by v square dou square f by dou t square will represent what? Will represent wave equation here. Will represent wave equation. Understood? Okay, so wave equation will looks like in this manner. Dou square f by dou x square is equal to 1 by v square into dou square f by dou t square. So this we call it as what here? Wave equation. Okay, so whenever we are dealing with electromagnetic waves, so in place of f here, in place of f, you are going to get what? Dou square E of what? E of x comma t, electric field, which is a function of x and t. Okay, so dou x square, which is equal to what? Which is equal to 1 by v square into dou square E of x comma t by dou t square. So in this manner we are going to get the wave equation. Understood? Okay, you can write in terms of magnetic fields also. Okay, in transmission lines, what you are going to get? Instead of electric field, what you are going to get? In transmission lines, you are going to get dou square v of what? Dou square v of x comma t by dou x square is equal to what? Dou square v of x comma t by dou t square into 1 by what? 1 by v square. Here this v is nothing but voltage here. This v is nothing but voltage, which is a function of x comma t. Understood? So this v is nothing but velocity. This v is nothing but velocity. So in this manner we are going to get the wave equation whenever you are dealing with uniform plane waves. So in this manner you are going to get the wave equation whenever you are dealing with transmission lines. Understood? Okay, so you have to understand that this represents what? This represents the wave equation, and wave equation will looks like in this manner. Okay, okay, okay. So how we are going to get these wave equations and all, we will study here. We will study as we proceed into the subject. Understood? Okay, okay. So now see here. So any function from where we got here, from where we got this wave equation. So from this wave function only, from this wave functions only, we have derived this wave equation. So that means wave function, that means which is of the form f of beta into plus or minus x plus or minus vt. So any function which is of this form has to satisfy what? Has to satisfy this wave equation. Yes or no? This is nothing but what? This is nothing but wave function. This is nothing but wave function. Right? So any wave function has to satisfy what? Has to satisfy wave equation. So definitely you can take any function here, any function which is of this form. Okay, so substitute in LHS side and substitute in RHS side. You are going to get what? LHS is equal to RHS. Definitely you will get the definitely LHS will become equal to what? Will become equal to RHS. Understood? So any wave function will satisfy what? Will satisfy this wave equation. So that means the solution of this wave equation will be like what? Will be like wave function. Understood? Okay, so this is how the solution of wave equation will looks like. Right? Okay, yeah. So now see here. Okay, so next we are I have told that throughout our subject we are going to deal with what? We are going to deal with time harmonic fields. We are going to deal with what here? Time harmonic fields. So what do you mean by time harmonic fields here? If the fields are varying, sinusoidally, with respect to what? With respect to time. So then those type of fields we call them as what here? Time harmonic fields. Okay, so I will take some examples here. We will take some examples, okay, and try to analyze that. Right? Okay. Funny. Good morning. What you are saying here? Banerjee, only 4 are watching. So it doesn't matter here. It doesn't matter how many persons are watching. Okay. So they may watch. More persons may watch later also. Right? Okay. So number of persons watching doesn't affect my lecture. Right? Okay. So our duty is to teach here. So we are ready to transmit. Right? Okay. And how many persons will take those things, it depends on you. It is not depending on us, right? Okay, so we will do our duty, that's it. Right, time harmonic fields. Fields are varying what? Fields are varying sinusoidally with respect to time. Then we call it as what? Then we call it as time harmonic fields, right? Okay. So example here, example, let us take some example here. So let us consider, I am considering some function which is a function of x comma t. So let us say I am considering it as some a into what? A into cos of beta into beta into vt minus x, beta into vt minus x. So this is of the form what? This is of the form f of what? F of beta into vt minus x. Yes or no? So I have considered this as what here? A sinusoidal function, a sinusoidal function. Okay. So if the function is varying sinusoidally with respect to time, then those functions we call it as what here? Time harmonic fields, time harmonic fields, right? Okay. Time harmonic fields, right? Okay. So a into cos of beta into vt minus x. So this is how we are going to represent the time harmonic fields. That means it has to vary with respect to time sinusoidally, right? Okay, yeah. So now see here. Now if you observe this function here, if you observe this function, I can write this one in this manner. A into cos of, I can write this as beta into v into t minus what? Minus beta into x, beta into x. Right. So here this a represents what here? A represents amplitude of the wave. A represents what here? Amplitude of the wave. Understood? Next, this total term here, this total term will represent what? Will represent phase of the wave. This total term will represent phase of the wave. Now you have to understand that this wave is a function of what? It is a function of both space as well as what? As well as time. So the function is oscillating with respect to time up and down, and these oscillations are shifting in x direction from one location to another location. Understood? Okay, so that means the phase is a function of what? Both space as well as what? As well as time. With respect to time, it is oscillating up and down, and with respect to x, that means these oscillations are shifting along what? Along x direction from one location to another location. Understood? So that's why it is having the phase. It is having the phase with respect to what? With respect to time. So this represents the phase with respect to what? With respect to time. With respect to time. Understood? And this beta x represents what here? Represents the phase. Will represents the phase with respect to what? With respect to space. With respect to space. Understood? Okay. So this will give you how the phase is changing with respect to what? With respect to space. And this will give you how the phase is changing with respect to what? With respect to time. Okay. So now if you want to observe the phase with respect to space here, if you want to observe the phase with respect to space, then in that case what we will do here is we will freeze the time here. We will freeze the time. So that means we will fix the we will freeze the time. That means we will make this vt some constant at some instant of time. Okay, so then if you make a vt some constant at that instant of time, you can observe what? You can observe how the wave is changing, how the phase of the wave is changing with respect to space. If you want to observe the change in phase with respect to space, then we are going to freeze what? We are going to freeze time. Similarly, if you want to observe how the phase of the wave is changing with respect to time, then in that case we are going to fix what? We are going to fix this location. So by fixing the space, you can observe what? You can observe how the phase of the wave is changing with respect to time. Similarly, if you fix time here, if you freeze time, then you can observe what? You can observe how the phase of the wave is changing with respect to space. Understood? Okay. Okay. Yeah. So now see here. So let us consider at some instant, let us say at t equal to 0, So that means here I am freezing time here. I am freezing time. Understood? So I am considering, I want to observe how the phase of the wave is varying with respect to what? With respect to space. So in that case, what I am doing here, I am freezing the time. So that means I am assuming at t equal to what? At t equal to 0. So at t equal to 0, how the function will looks like here? So a into what? A into cos of minus beta x. I can write it as what? Simply cos of beta x. Yes or no? Cos of minus theta is cos theta. So in that manner, I can write cos of minus beta x. I can write simply as a into cos of beta x. Understood? Now, if you observe this function here, if you observe this function, okay, so this is along x, this is along x, right? Okay. Okay. So here this is 0. So let us consider this axis. I am considering beta x here, beta x. So here this is pi by 2. Let us say this is pi, and let us say this is 2 pi. Okay. Okay. So this is pi by 2, and here it is pi. Wait. Sorry, this is 3 pi by 2 here. This is 3 pi by 2. 3 pi by 2. So here it is 2 pi, here it is 2 pi, right? Okay. So this is how the phase of the wave is changing with respect to time here. So this is nothing but a into cos of beta x, a into cos of beta x. Okay. So this is at what here? At time t is equal to 0. At time t is equal to 0. At time t is equal to 0. So this is how the phase of the wave is looking like. This is how the phase of the wave is looking like. Understood? See, the distance from here to here, the distance from here to here is nothing but what? Is nothing but lambda. Yes or no? So it covers lambda distance over one complete cycle. It is going to cover lambda distance over one complete cycle. Understood? Okay. So that means here here that means the phase of the wave at this location here, at this location, the phase of the wave at this location at 2 pi. Okay. So that means at 2 pi here, at 2 pi. So at 2 pi, at 2 pi, at 2 pi. So that is okay, wait. Okay. So at 2 pi here, at 2 pi, what is the distance it has covered here? What is the distance it has covered? Whenever beta x is equal to 2 pi, whenever beta x is equal to 2 pi, what is the distance it has covered? It has covered lambda meters. It has covered lambda meters. Yes or no? So that means at x equal to lambda here, so this distance is nothing but what? Lambda meters. So at x equal to lambda, what is the change in phase? So the change in phase is nothing but beta x. In place of x, I am writing it as what? I am writing lambda, which is equal to what? Which is equal to 2 pi, which is equal to 2 pi. So at x equal to lambda here, at x equal to lambda, what is the change in phase? What is the change in phase? So as you move from here to here, as you move from here to here, that means over lambda meters, what is the change in phase here? Change in phase is how much? 2 pi. Understood? Okay. So this beta x here, this beta x will give you what? Will give you the change in phase, will give you the change in phase along what? Along x, along x. Understood? Beta x will give you the change in phase along x. So if you move lambda meters, so that means x equal to what? X equal to lambda. So over lambda meters, what is the change in phase along x? Over lambda meters, what is the change in phase along x? So that is nothing but what? That is nothing but 2 pi. So beta lambda is equal to what? Is equal to 2 pi. So therefore beta is equal to what? Therefore beta is equal to 2 pi by lambda. Beta is equal to 2 pi by lambda. So what are the units of beta here? So 2 pi is radian, lambda is meters. So beta is equal to 2 pi by lambda, radian per meter. So this beta, we call it as what here? We call it as a phase constant. We call it as what? Phase constant. So it is giving, so beta, we call it as what? We call it as phase constant. Understood? Okay. Okay. So it tells us about the change in phase, the change in phase with respect, the change in phase per meter. It represents the change in phase per meter. Okay, change in phase per meter with respect to what? With respect to space. With respect to space. Right? Okay. So beta we call it as what here? Phase constant, and what it is going to tell you here? It is going to tell you the change in phase per what? Per meter. Right? Okay. Okay. How the phase of the wave is going to change for every meter. So that's what this beta will represent. So beta is equal to what? Beta is equal to 2 pi by lambda. Beta is equal to 2 pi by lambda. Right? Okay. So it represents how the phase of the wave changes. How the phase of the wave changes for every meter. For every meter. Okay, how the phase of the wave changes for every meter. Understood? Now, what this beta x will represent here? What this beta x will represent? Beta represents how the phase of the wave changes for every meter. Beta x represents what? Beta x represents the total change in phase. Yes or no? Beta x represents total change in phase. Total change in phase over what? Over x meters. Over x meters. So beta x will represent the total change in phase over what? Over x meters. So if you travel x meters, then what is the total change in phase with respect to x? So that is given by what? Beta into x, where beta represents the change in phase per meter. Beta x represents the change in phase over x meters. Understood? Okay. Okay. So now see here. So we have drawn the diagram like this. Yes, sir. Now we have taken cos function. We have taken cos function something like this. Understood? Okay. 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 So this is at what here? This is at t is equal to 0. At t is equal to 0, a into cos of beta into Vt minus x. So we got at Vt equal to 0, we got simply a into cos of beta x. So this is what we have drawn here. So this is nothing but a into cos of what? Cos of beta x. Right. Okay. Now let us consider at some other instant of time here. Let us consider at omega t, at some other instant of time, such that at that instant omega t has become what? Omega t has become 90 degrees. Let us assume. Okay. So in this case, how the function will look like here? So a into what? A into cos of what? A into cos of what you are going to get here? You are going to get beta, sorry, here it is wait. Okay, so here you can consider at some other instant of time here. Let us consider a into cos of, I am writing this as beta Vt minus what? Minus beta into x. Beta Vt minus beta into x. Okay. So now I am considering at some other instant of time such that at that instant beta Vt, at that instant beta Vt is becoming equal to what? This beta Vt is becoming equal to 90 degrees. So in that case, what you are going to get? In that case, so I am choosing at some other instant of time, at that instant the phase, this beta Vt is becoming equal to what? Is equal to 90 degrees at some other instant of time I am considering. So in this case, what you are going to get? Cos of what? Cos of 90 minus what? 90 minus beta x. So this is equivalent to what here? I can write this as what? A into sine of what? A into sine of beta x. Understood? Okay. So after some instant of time here, after some instant of time, at that instant of time, beta Vt is equal to what? Is equal to 90 degrees. At this instant of time, I got the function as what here? A into sine of beta x. A into sine of beta x. So that means I can draw this diagram in this manner here. Right? See here. See, this is at beta Vt is equal to 0. Understood? Okay. So now whatever the diagram I am drawing, so that is at beta Vt is equal to what? 90 degrees. So at 90 degrees we are getting what here? Sine function. So just try to draw that sine function here. Right? Okay. So here right? Okay. Okay, so sine function you are going to get okay. Okay. So now, so this is at beta Vt is equal to at some instant here, at some instant, that is beta Vt is equal to 0. Now this is at another instant, this is at another instant I have drawn. So that is at beta Vt is equal to what? Is equal to 90 degrees. At some other instant I got the function in this manner. Right. Okay. So now if you observe, what is the difference between this one and this one here? This is at some instant I have drawn how the wave is changing with respect to space, and at some other instant I have drawn how the wave is changing with respect to what? With respect to space. Now if you observe here, if you observe, so this one I can extend like this, see here. Now if you observe here, so at this instant, okay, so the wave is like this, yes or no? Now after some instant at beta Vt equal to 90 degrees, this point has moved to this location, yes or no? Next, this point has moved to what? Has moved to this location. Next, this point has moved to what? Has moved to this location, and this point has moved to this location, and this point has moved to this location, and this point has moved to this location. So this point has moved to this location. So similarly this one moved to this one. So this point has moved to this location. So this point has moved to this location. Understood? So what you can observe here from this? So the wave, so at this instant, this is the wave function you are having. Understood? So at some other instant, after some other instant, what is happening here? This wave is shifting towards what? Towards right. See, if you observe all the points here, all these points are moving towards what? Are moving towards what? Are shifting towards what? Are shifting towards x here, towards positive x direction. Understood? So next, if you take another instant of time, this total wave function is going to shift further along what? Along x. Understood? So if you freeze the time, you can observe the spatial variations of the wave with respect to what? With respect to space. Understood? You can observe the spatial variations of the wave with respect to what? With respect to x or with respect to space. Understood? Okay. So by freezing the time, you can observe what? You can observe the spatial variations of the wave. Understood? Okay. Now similarly here, Similarly, if you freeze space here, if you fix some location, then you can observe what? You can observe how the wave is, how the phase of the wave is changing with respect to what? With respect to space, with respect to time, sorry. Okay. So now take the same function here, a into cos of what? Cos of beta Vt minus what? Minus beta x. Okay. Now let us consider at x equal to 0 here. Okay. So at x equal to 0, or you can consider simply beta x is equal to 0. Understood? So at this location here, if you write the wave function, you are going to get what? A into cos of what? A into cos of beta into what? Beta into Vt. Understood? See, suppose that means if I am drawing a wave, I am considering a wave like this, right? Okay, I am considering a wave like this, right? Okay. Okay. So this axis I am considering as beta x here, let us consider, right? Okay. Next, so here So here I am considering the plane. I am considering a plane. So this plane is nothing but what? Transverse plane here. This plane is nothing but transverse plane, right? Okay. Okay. So let us say this location is x is equal to 0 location. This location is x is equal to 0 location, right? Okay. Okay. Yeah. Oh, wait. Okay, so now here I have fixed the location here. I have fixed the location x is equal to what? X is equal to 0. At x equal to 0, beta x is equal to what? Beta x is equal to 0. Okay, so at this location I have drawn what? I have drawn a transverse plane. I have drawn a transverse plane. Okay, so now I am going to observe what? I am going to observe how this function is going to vary with respect to what? With respect to time. So that means how the phase of the wave. This is nothing but phase with respect to what? With respect to what? With respect to time. How the phase of the wave is changing with respect to time. That's what I want to observe. Okay, so now if you observe at x equal to 0, so for this what I have done, I have fixed the location here. This is the location I have fixed. Understood? Okay, now at some instant t is equal to 0 here, such that beta vt is equal to 0. Beta vt is equal to 0. This function will be what? This function will be maximum. So at this location I have drawn some transverse plane. So at some instant of time, this function is having what? Is having the maximum value. So this is at what? This is at beta vt is equal to what? Beta vt is equal to 0. So next, after some time, what will happen here? After some time, we have seen that this wave is going to shift further. Yes or no? This wave is going to shift further along what? Along x. Yes or no? So if this wave shifts further, I am fixing this location here. I want to observe. I am going to observe how the field is varying with respect to time. I want to observe how the field is varying with respect to time. So for that I am fixing this location. So my observation will be at this location here. Understood? We know that with respect to time, this function is going to shift what? This function is going to shift towards what? Towards right. So as this function shifts towards right, what will happen here? For next instant of time, this point here, this point of the wave is going to reach what? Is going to reach to this location. Yes or no? This point of the wave is going to reach, this point is going to reach what? Is going to reach to this location. So I am standing here and observing in the transverse plane. Understood? How the phase of the wave is changing with respect to time. That's what I am observing. So as time progresses, we know that this wave is going to shift what? This wave is going to shift further. Understood? Okay, so at that time what will happen here? This point is going to reach to this location. Next, what will happen? This point is going to reach what? Is going to reach to this location. Next, after some time, this point will reach to this location. After some time, this point will reach to this location. Again, this point will reach to this location. This point will reach to this location. This point will reach to this location. Again, this point will reach to this location. So that means in this transverse plane, if you observe initially this point is at this location. Next, after that what happened here? What happened? So this has moved to this location. Next, after that this has moved to this location. After that this has moved to this location. After that this has moved this location. Next, after some time what will happen? This again has moved to this location. 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 Understood? So that means if you observe in this transverse plane here, what you can observe with respect to time here? With respect to time. So with respect to time, if you observe, this particle is simply oscillating up and down. Yes or no? That's what I have told now. So in a transverse plane, you are going to have what? You are going to have the oscillations with respect to time. Understood? So these oscillations are going to shift from one location to other location. Understood? Okay, so this is how the particle is oscillating with respect to time. Understood? Okay, so if you want to observe the time variations, what you have to do here? You have to fix some location. So at that location, I have drawn what? I have drawn a transverse plane. Understood? Then with respect to time, if you observe at this location, what you can observe here? You can observe that the particle is simply oscillating up and down. So these are the variations with respect to what? With respect to time. And here we have observed that this is the variations with respect to space. Understood? So as time progresses, this wave is going to shift further. So this is at beta vt is equal to 0. This is at beta vt equal to 90 degrees. So the wave is shifting further. So as the wave shifts further towards x direction, what will happen in this plane? So the particle is going to oscillate up and down. Okay, so this is how you have to observe what? You have to observe the time variations with respect to space and time variations. This is how you have to analyze the time variations. Understood? Okay, the change in phase with respect to time. So for that, what you have to do? You have to fix the location, and at that particular location you have to observe how the particle is oscillating with respect to time. Understood? So now, if you want to analyze the spatial variations, then you have to fix what? You have to fix the time, and then you have to analyze what? You have to analyze the spatial variations. So you have to understand that whenever we are representing a wave function, it is going to have phase. That phase is a function of what? Both space as well as what? As well as time. So if you want to analyze the phase with respect to space, then you have to fix time. If you want to analyze the phase with respect to time, then you have to fix what? You have to fix the space. Understood? Okay, so this is what you have to understand, right? Okay, yeah. So I hope this point is crystal clear here. I hope this point is crystal clear, right? Okay, okay, yeah. So now see here. So the same analysis we can take by taking a into sine of beta into vt minus x, like that. Okay, any sinusoidal function you can analyze in the same manner. Okay, so we have considered a into cos of beta into vt minus what? Vt minus x, right? Okay. Okay, yeah. So we have determined this beta value here. Beta is equal to what? We got beta is equal to 2 pi by lambda. Beta is equal to 2 pi by lambda. Okay. So now what is beta into vt here? What is beta into vt? What is beta into vt? Tell me. See here. How we can represent this beta into vt? See here. See, if I fix a space here, let us say x equal to 0, then this function will become a into cos of beta into what? Beta into vt. Now if I draw this function with respect to time, now I am considering this axis as what? This axis as beta into vt with respect to time. If I draw this function, so this is the function I am going to get. Understood? Okay, so some cos function I have drawn with respect to what? This is with respect to time. Understood? So from here to here, what is the change in phase here? What is the change in phase from here to here? What is the change in phase? The change in phase is nothing but what? Is nothing but 2 pi radians. So it is completing one cycle, so we can call it as what? This is nothing but what? This is nothing but time period. This is nothing but time period. Yes or no? So from here to here, it has completed one cycle, so we call that as what? We call that as time period of the signal. Yes or no? Okay, so within time period t, what is the change in phase with respect to time here? The change in phase with respect to time is how much? Is 2 pi radians. Yes or no? So that means at t is equal to t, so this beta v into t has become equal to what? Will become equal to 2 pi. Yes or no? This is with respect to time here. This is with respect to time we are dealing. Understood? So beta vt is equal to what? Is equal to 2 pi. So therefore beta v is equal to what? 2 pi by what? 2 pi by t. We know that 1 by t I can write it as what? F. 1 by t I can write it as f. So that is 2 pi f, which is equal to what? Which is equal to omega. So that means therefore beta into v I can represent it as what? I can replace it with omega here. Beta into v I can replace it with omega. Right? Okay. So from here, if you want the velocity of the wave, v is nothing but what? Velocity of the wave. So the velocity of the wave, if you want, you can write v is equal to what? Omega by what? Omega by beta. Yes or no? See, the units of omega is radian per second, and the units of beta is radian per what? Radian per meter. Yes or no? Beta value is nothing but what? 2 pi by lambda, radian per meter. So here radian will get cancelled. What you are going to get? Finally, you are going to get meter per second, the units. That is nothing but units of what? Velocity. So this gives you the velocity of the wave. Okay, so you can replace beta v with what? Beta v with omega, and the velocity of the wave we are getting as what? Omega by beta. So if you take the ratio of omega to beta, that is going to give you what? That is going to give you the velocity of the wave, right? Okay. Okay. So therefore velocity of the wave V is equal to what? V is equal to omega by beta meter per second, meter per second. Understood? Okay. So if you know omega value, if you know beta value, then you can determine the velocity of what? The velocity of wave. And beta v we can replace with what? We can replace with omega. So that means A into cos of beta into what? Beta into Vt minus x. I can represent this as what here? I can represent this as A into cos of beta into V. Beta into V is nothing but what? Beta into V is nothing but omega. Yes or no? So I can write this as omega t minus what? Minus beta x. So in this manner I can represent the wave. Yes or no? Okay. Okay. So this wave, we call it as what here? Time harmonic, because it is varying with respect to time sinusoidally, right? Okay. Okay. So where omega is nothing but what? Omega is nothing but beta into what? Beta into V. So this is how we can represent. So similarly here, we can represent, or you can represent in terms of what? In terms of sign also. Sign of omega t minus beta x. Omega t minus beta x. So this type of waveforms here, are called as real time time harmonic fields here. We can call them as real time harmonic fields. Okay. Or you can call it as a you can simply call it as a real time solutions here. Real time wave functions. Yes or no? Okay. And this wave function we have considered as what? Time harmonic fields. Understood? Okay. So you can represent the wave functions in real time expressions in this manner, either in terms of cos or in terms of what? Or in terms of sine. Okay. So you can represent the same time harmonic fields in terms of what? In terms of complex form also. Understood? Okay. So how you can represent here in complex form? I can represent as a into, let us say, A of x comma t is equal to what? Is equal to A into e power j of what? E power j of omega t minus what? Minus beta x. So this is also of the form what? This is also of the form this field is also varying with respect to time sinusoidally. So we can call this as what? Time harmonic fields. Understood? Okay. So in complex form, if you want to represent in complex form, you can represent in this manner. Understood? Okay. So this is also sinusoidal variation only. So sinusoidal variation in complex form, and this is a sinusoidal variation in real form here, in real time. You can have sinusoidal function, cos function and sine function. Yes or no? These are called as, generally these are called as real time solutions for a wave equation. Understood? And this is nothing but what? This is nothing but complex form of the time harmonic wave. Understood? Okay. Okay. So now see here. Now in general here, whenever we are writing the wave function in general, let us say A into cos of omega t minus beta x. Understood? So in general, this wave can have what? Can have some phase shift. So that phase shift is nothing but what? Let us say that is phi. Understood? That means at t is equal to 0 and x equal to 0, if there is no phase shift here, if phi is equal to 0 degrees, then at t equal to 0, x equal to 0, we know that this cos function is going to be maximum. Okay. But if there exists any phase shift, understood? So at t is equal to 0 and x equal to 0, the function is not making maximum. In that case, we can say it is having some phase shift phi. Understood? Okay. So the initial phase shift of the wave is nothing but phi. Understood? So this is the general representation here. This is the general representation. In general representation, we can include what? We can include this phase shift also. Understood? That means at x equal to 0 and t equal to 0, this wave may have what? This wave may have some initial phase shift. Okay. So the function may not be maximum at x equal to 0 and t equal to 0. It is having some phase shift here. So this is the general representation. Understood? Okay. Or in terms of sine also, you can represent A into sine of what? Omega t minus beta x plus what? Plus phi. Understood? So this is the general form of what? General form of real time waveforms. Okay. Okay, yeah. So in general representation in complex form, how you can represent a of x comma t is equal to what? A into e power j of what? E power j of omega t minus beta x. So generally it may have what? Some phase shift. Let us say that phase shift is phi. Understood? But whenever you are representing in complex form here, whenever we are representing in complex form, we will represent in this manner. So that is a into, I can write this as what? A into e power j phi into what? Into e power j of omega t minus beta x. Now if you observe, this is nothing but what? This is nothing but amplitude. Yes or no? So this amplitude in general, is what here? Is a complex quantity. Yes or no? A into e power j phi means this also what? This is also a complex quantity. So in generally whenever we are representing here, a into e power j of omega t minus beta x, in general, let us say I am representing this amplitude with a dash here, a dash. Understood? Where this a dash in generally is nothing but what? A into what? A into e power j phi. You have to understand that in general the amplitude can be what? The amplitude can be a complex quantity. Understood? Okay? Okay. So this is nothing but what? This is whenever you are representing the waveform in complex form. Understood? Okay. Okay. So in generally whenever we are representing in complex form, you have to understand that the amplitude in general, the amplitude of the waveform in general is what? Is a complex quantity. Understood? Okay. 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 So I hope all these things are crystal clear here. Right? Okay. So we have studied about what? We have studied about how to represent the wave function and what do you mean by transverse wave and how to represent the transverse wave mathematically. Understood? And then we have seen how to analyze this phase of the wave is going to have this phase of the wave is a function of what? Both space as well as what? As well as time. How to analyze the spatial variations and how to analyze the time variations. So all those things we have seen here, and also we have seen the general representation of the waveforms in time harmonic case. Understood? Okay. Okay. So next we will start with transmission lines. Okay. See, in order to understand these transmission lines are uniform plane waves, so whatever the topics that we are going to cover, okay, so this will form here, this nature of the wave and how these waveforms will look like. So all these things will put a strong foundation for us to analyze and understand the further topics of the subject. See, in uniform plane waves you are going to study about the traveling waves, and in transmission lines you will get what? You will get standing wave patterns on the transmission line. We will analyze that standing wave pattern and all those things also. Okay. Next, once you enter into waveguides, there you are going to get the combination of traveling wave pattern as well as what? Standing wave pattern. Understood? Okay. So that's why understanding the nature of the wave is very, very important, right? Okay. Okay. So next we will start with transmission lines here. So a transmission line is nothing but what? Is nothing but a guiding structure. It is one of the guiding structures that we are going to study. So it is going to guide the signal from where to where? From source to load. Understood? Okay. So we are having different types of transmission lines here. So that is just I am drawing the diagram here. So you can have power transmission line here. You can have power transmission line. So a power transmission line can be assumed as what? Two conductors. We are going to have two conductors separated by what? Separated by some dielectric medium. Okay. So this is power transmission lines here. So these are going to operate at what? Here you are going to have one conductor and another conductor separated by what? Separated by some dielectric medium. So in generally these power transmission lines are operated at what here? Are operated at 50 Hz or 60 Hz in this range. Okay. In US or something other other states, that means in foreign they will use what, 60 Hz. In our India we are using what, 50 Hz. Understood? So this is operated at what? This is operated at low frequency, This is one type of transmission line. So next we are having another type of transmission line. So that is coaxial cable, right? Okay. So you are going to have the coaxial cable like this. So inside you are going to have conductor, and outside also conductor, and between these two you are going to have what? You are going to have dielectric medium. Understood? So inside you are going to have conductor, above that what you are going to have? Dielectric material. Above that dielectric material, again you are going to have conducting structure. Above that you are going to have what? You are going to have the shielding. Yes or no? That is also dielectric. Understood? Okay. So that is how the coaxial cable will looks like. Understood? Right. Okay. So this is coaxial cable. Right. So it is going to operate at what here? It is going to operate in the range of megahertz here. Megahertz to gigahertz. Understood? Coaxial cable, somewhat higher frequency range. Understood? Next we are having another type of transmission line here. So that is microstrip transmission lines. Okay. Okay, so this is microstrip transmission line. So this is operated in gigahertz range here, and it may be above gigahertz also. Okay, so it is utilized at what? In the range of what? In the range of gigahertz. So it is from megahertz to gigahertz. So it is operated, microstrip transmission line is operated in gigahertz range. Understood? See, whatever the part that I have shaded here, is nothing but what? Is nothing but conducting region. And between these two conductors here you are having a conducting region, Between these two, whatever that is present, that is nothing but what? That is nothing but dielectric region. Understood? Okay. So this is microstrip transmission line. So you are having different types of transmission lines here. One is power transmission line, which is operated at what? Which is operated at very low frequencies. And you are having another type of transmission line. So that is nothing but what? That is nothing but coaxial cable, which is operated between what? Between megahertz to gigahertz. And we are having another type of transmission line, which is called as what? Which is called as microstrip transmission line, which is operated at very high frequencies, that is in the range of what? Gigahertz. Understood? Okay. So if you observe all these transmission lines here, all these different types of transmission lines, if you observe, what you can observe here? See here you are having a conductor, two conductors separated by what? Separated by some dielectric medium. And if you observe this one, coaxial cable, here also what you are having here? Here inside you are having a conductor, and outside here you are having a conducting medium. So between these two conductors, what you are having? You are going to have a dielectric region. Understood? Okay. So two conductors, and in between those two conductors we are having what? We are having a dielectric medium. And if you observe microstrip line also, what you can observe here? Here you are having conducting region, and below you are having another conducting region. Between these two you are having what? You are having a dielectric region. So what is the common property of all these transmission lines here? What is the common property of all these transmission lines? So you are having two conductors. Yes or no? You are having two conducting, you are having two conductors separated by what? Separated by some dielectric medium. Understood? So if you observe, for all these different types of transmission lines, what we can observe here is, for each and every structure we are having two conductors, and they are separated by what? They are separated by some dielectric medium. They are separated by some dielectric medium. So from here onwards, we are not going to study particularly, about any type of transmission line. That means we are not going to study particularly about power transmission line, or we are not going to study particularly about coaxial cable, or we are not going to study particularly about microstrip line. We are going to study the transmission lines in general. Understood? See, what is the general property of all these transmission lines? You are having two conductors separated by what? Separated by some dielectric medium. So we are going to analyze the transmission line such that it is going to have what? It is going to have two conductors separated by what? Separated by some dielectric medium. At one end we are going to connect what? At one end we are going to connect source. At one end we are going to connect source, and at another end we are going to connect what? We are going to connect some load. Understood? Okay. So in this manner we are going to analyze the transmission line. Okay. So we are going to study about the transmission lines in general. Okay. So that means it is not particularly related to any type of transmission line here. Okay. In general we are going to study about the transmission line. So that's why we are going to consider our transmission line as what here? Two conductors separated by what? Separated by dielectric medium. See, it is just like we are going to analyze the characteristics of human beings. If I say we are going to analyze the characteristics of human beings, means we are going to study about the characteristics in general. How the human beings will behave like that. Okay. We are not going to study particularly about a single person, right? We are going to study the total human being. We are going to study the general characteristics of all the human beings, not about a particular person. Understood? In the same manner here also, we are not going to study particularly about particular transmission line. We are going to study the transmission line general characteristics. Understood? General characteristics of a transmission line. Okay. So in general we are going to study the transmission line, right? Okay. So wherever it is needed here, we can touch somewhere coaxial cable. Power transmission lines, it is not in our region. Microstrip also, it is not in our region. So if possible, so we can touch this coaxial cable, right? Okay. So this power transmission lines you will study in electrical, right? Okay. In microstrip transmission line you will study in microwave engineering, right? Okay. So in general here we are going to study the general characteristics of a transmission line. We are going to treat the transmission line as two conductors separated by some dielectric medium, and here you are going to connect some source, here we are going to connect some load. So we are going to transmit the signal from source to load, and here this acts as what? This acts as a guiding structure. So this guiding structure, we are calling it as what? We are calling it as transmission line. That's it, right? Okay. So I will give you one question here, right? See, in general, whenever you are dealing with circuit theory here, so let us say here V of t, and here you are having some resistor R, right? Okay. So whenever you are dealing with circuit theory, so always you will represent voltages and currents. Whenever a sinusoidal signal is applied, then always you will represent voltages and currents as a function of what? As a function of time. Right? Okay. Now whereas whenever you are dealing with transmission lines here, then you are going to represent the voltages and currents here, as a function of what? As a function of space as well as what? Space as well as time. So that means you are going to consider the length of the transmission line also. So if you include the length of the transmission line, then the voltages and currents on the transmission line will become functions of what? Both space as well as what? As well as time. But here you are not going to include, here this is the length of the circuit, but you are not including the length of what? The length of the circuit. You are neglecting this length of the circuit, and we are considering only what? Time variations of voltages and currents, whereas here we are considering the both time variations as well as what? Spatial variations along the transmission line. Okay. So why we are considering this? Why not we are considering here spatial variations? Understood? So this is all because of transit time here. Understood? Okay. So So that one we will it will take more than half an hour or 1 hour here, right? Okay, so that's why I'm going to deal that topic in the next lecture, right? So this is because of what? Why here they have become a functions of both space and time? Why here we are not considering it as a function of length? Why we are considering only a function of time? So this is all because of what? This is all because of transit time effects. This is all because of transit time effects. So what do you mean by transit time, and what are its effects, right? So all those things we will study in the next class here, in the next class, right? Okay, okay. So just revise whatever we have done, that is nature of the wave, and how the wave functions will look like, and how the wave equation will look like. So all these things please revise before coming to the next class, right? Okay, so in the next session we will deal with transit time effects, right? Okay, okay. So once we complete the transit time effects, then we will see distributive nature along the transmission line. So these two concepts will play a very important role in understanding what? In understanding the transmission lines, right? Okay, okay. So with this I am ending up the session. Just I have given some introduction to transmission lines today, and from tomorrow we are going to enter into the exact topics here, that is transit time effects. Understood? Okay, okay. So with this I am going to end up the session. So tomorrow here, tomorrow at 10 AM, right? So daily here, daily in our Gate Academy Global channel, EMT class will be conducted daily at 10 AM, right? Okay, so tomorrow also the class will commence at 10 AM here, right? Okay, okay. So we will meet tomorrow exactly at 10 AM in our Gate Academy Global channel, right? Okay, okay. So until then, take care. Bye bye.